this week's CRM seminar. We have the great pleasure of having our very own Nicolas Crampe, who is here visiting us. As many of you know, he works with Luc Vernet on topics in mathematical physics involving subjects from beta ansatz, Raka algebra, and also today's subject, which will be on solitons. So Nicolas will be talking about absorption or emission of solitons. So thank you very much, Nicolas, and please go ahead.
So thank you very much. So yes, so that is not an unusual subject for me. In fact, if the people who know me, it's more, I prefer algebra and something like that. But okay, it's something I found quite recently with my friend Vincent Caudrelier from the University of Leeds and Carlos, which is the PhD students. So, and in fact, the questions come from algebra somewhere. When we start to discuss about this subject, it's really solve some problem in algebra, and I asked Vincent how to deal with that with solitons. And so we arrive to this type of picture. So the left-hand side picture is the usual things. So you have, that is really the x position, the position of the wave and the time. So that is really the wave which is go through the canal, if you want, and they cross, and you have a reflection, a pure reflection on it. That is the usual thing that it was known previously than us and very well studied. And in our case, we are in some particular speed, the soliton can disappear on the boundary. So it's really the subject of this talk. It's to present you how we arrive to this type of boundary in classical integrable systems. So maybe just, so that is my outline. So I will discuss a bit about soliton just because it's a nice picture, and for one time I can make physics and show nice picture. So that will be my introduction somewhere. And after I go on in the particular integrable system, which is the Ablovitz-Ladik model. So I will introduce that and how to prove the integrability. I will explain you how we can introduce boundaries and particular boundaries which still remains integrable. The model remains integrable after this boundary. I will introduce the time-dependent boundary, which I'm interested in, and I give you the solutions. So what are the solitons? So that is really, it has been discovered in 1834 by an engineering, and it's in this canal in UK, and you see the wave in front of the boat, and they go, the guy which discovers that say for kilometers the wave remains unchanged on the canal, it doesn't change. So that is really the first wave, the first times in the literature the soliton wave appears. And now I think 100 years after, we can understand that theoretically. So that is really, you have your two waves, they're moving, and you see the smallest one go faster. And what is quite incredible with this wave, they are not deformed when they move, but also when they cross. So here you see you have an interaction between both waves, but after that, the other wave is not deformed at all. And the way I represent that will be like in my first slide, I will represent like that. So that is really where are the wave in the X and T axis. It will be easier for me to present all the solutions like that. And just to give you an idea of how it's complicated, so explicit, it's really an explicit formula, and it's given like that. I don't write everything, but just to give you an idea, you have only two solitons, and it's quite complicated analytical expression, but it is an explicit solution of that. So what is quite amazing, so I can just show you really what I show you here when the wave cross. In the real life, it works. So that I can show you some movie. So it's why, so that is an aquarium, and you will going to see, so maybe I must switch of the sound. So you see the wave which appears. So, and you see the wave doesn't deform when they move. They go on, like you see, nothing move. There are reflections. They send another wave, and they are going to cross. And you be careful because it's quite. You must look at it, but okay, they cross, and they go on. So maybe I can show you again because I like this movie. Oops. That doesn't cross and that doesn't change. So I found that quite things nice. So that just very informally, what is a solitons? So we can go now to maths, and I can explain you how we can find theoretically the solution of this type of models. So the model I'm interested in will be the Ablovitz-Ladik models. So I have complex functions depending on one continuous variable t, which is if you want the time, and j, which is some integer, which is the position. So it's a discrete positions. It's that j is integers, so it's a discrete positions. And the equation of motions of these functions is given by that. So I is a complex number. Q dot, the dot is the derivative of time as usual. So I don't write at each time, it's depending on t here, but I don't write it. You have these things, which is, you can look at it and it's a discrete Laplacians. If I send one is h bar or epsilon and I send epsilon to 0, that becomes the Laplacians. These things here. And we have a non-linear interactions between the functions at the side j and the function at the side j plus 1 and j minus 1. So that is known also like is also called discrete non-linear Schrödinger equations. So, and it's integrable. So what I'm going to show you now is how to show this model is integrable. So maybe for the people who don't know, integrable in this sense, it's really in the sense of Liouville, meaning I'm going to show I have some conserved quantities with time, the conserved quantities with this equation of motions. So before that, I need an Hamiltonian formalism for this equation of motions. And so the Hamiltonians of this model is just given by that. So I sum over j, the sides, q star of j, qj plus 1, and we have the logarithm of 1 minus qj square, which is the interaction terms. That will give you only the Laplacian terms, and that gives you the interaction terms. My Poisson bracket is not canonical. It's easier to deal with non-canonical Poisson bracket. So here qj, qk, Poisson commutes, but here I have qj, qk star, Poisson commute with some terms 1 minus qj square. And it's just an easy computation. Taking this Hamiltonian with this Poisson bracket, I recover the equation of motion here using the Hamiltonian equations. So my model, my Ablovitz-Ladik model, can be rephrased in the Hamiltonian formalisms. So a bit more complicated things is, okay, I need also the lag spec to prove the integrability. So now that I introduce the matrices, where Z is a complex number, if you want, or an abstract object, if you prefer. You have the field inside here, qj, qj star, and with some normalizations. We introduce also these R matrices here. And one thing nice is just the Poisson bracket between the field is equivalent to these equations. So that I take the Poisson bracket of these two matrices, that is these terms, and that gives you exactly all these terms here. So that is very well known. It's very useful for this context in integrable systems. Now, using this small l, I introduce just here, containing the field. So this L of j contains the field as a side j, and I multiply, all this L on different sides, the side 0, 1, n-1, up to n. So that is still a 2x2 matrices, but quite complicated because you have all the multiplications inside it. I take a trace that is called the transfer matrices. Okay, so I have a 2x2 matrices containing my field. I take a trace and I can show, just using the fact the L satisfies these relations, I can show this transfer matrix Poisson commutes for different spectral parameters. That is also very well known. And what is nice is inside the expansions in Z, we have H, the Hamiltonian of our model. So if to go back, we get exactly these terms here. Somewhere, it's quite explicit, but I don't want to write all the formula, but somewhere in these expansions, H appears. So I have H, which commutes with all these polynomial on W. So I have all the conserved quantities. And if you count it, it's exactly the number n plus 1, which is the number of conserved quantities we want to say it's integrable. So that is a way to prove Ablovitz-Slavic model is integrable. So that's for segment, for periodic boundary conditions. So that means because of the trace, the site n sees the site 0. So it's really on the circle. If I want now to put some boundary, so I want some segment with particular boundary, that things we need know what is done by Sklianin works in 87. So I need a new object. So R matrix is the usual one. Is the one I gave you previously. It's exactly this R matrix. That is a 4x4 matrices. I know it, no problem. And I solve this equation. So I solve this K matrices is a 2x2 matrices, and I solve these equations. So, okay, it's just some matter of time to find the solution of that, but it's not so complicated. I recall you the single row transfer matrices. That is a product of the small L matrices containing all my field. And now, instead to doing just the trace on that, I make what we call the double row. Meaning I take this L, which is the product here. I take two solutions of this equation, K plus and K minus, and I multiply by L, this 2x2 matrices inverse taken in 1/z. I take N, I will take the trace. That will be called, I will be called that double row transfer matrices. And thanks to these equations, thanks to the equation satisfied by the small L, I can again show the BZ and the BW Poisson commutes. So that it will be the two solutions of the reflection equation I will use. So again, the reflection equation is these equations. So I can show these 2x2 matrices is a solution of the reflection equations. And you see you have now 4 parameters here in these K matrices. And again, by expanding the transfer matrices, the double row transfer matrices here, I can show somewhere in the expansion on Z, there is what I will call an Hamiltonian, which is that. So that part is the one we know that will give me the three things. It will give me the Laplacians. That is the usual things also is the interactions on the bulk. But I have new terms appearing here where so it's a Q star here, R is Q star and R1 is Q star 1, where we deal only with the field at the site 0 and the field at the site 1. And it's given by something not complicated, but okay, you just compute it. And the parameters in these K matrices, A, B, C, D, appears in this term. A, D is here, B is here, and so on. So again, if I look for the equation of motion of that, I will get that. Okay, I have an Hamiltonian. I have my Poisson bracket doesn't change. It's still the one with the 1 minus q square, but my Hamiltonian change, and I get this equation of motion. So in the bulk means J is 2 up to n minus 1. My equation of motion doesn't change in the usual one of Abovich-Slavic model. But at the boundary, I have quite complicated terms where, again, here we saw something like a Laplacian, but you see you have a -2 here, it becomes a +1, and you have a terms containing the ABCD. But this model is still integrable. So previously, people study the things where C and D is equal to 0. That it was well known. And if C and D is equal to 0, the solution is the one I showed you previously, where they reflect on the boundary. And our goal here was to say, okay, no, we want to find solutions with C and D are different on 0. And usual technique with this equation of motions seems not so well. We don't succeed in using the usual method to solve and find soliton solution for that. So before that, we are going to show this model will be equivalent to another one with time-dependent boundaries. So that is integrable, everything nice, but it's just complicated, and we don't have the techniques to find the soliton solutions for this type of boundaries. So we make a change of variables. So that is a trick. So instead to have the field Q naught, I use the big Q naught here. So again, C, N, A, and D are the parameter of the boundary. And big Q for the other side is just small q. So I just change the field at the site 0. And if I did that, something happens quite nicely, because now the equation of motions is everywhere the same. And I have a boundary conditions, just one more given by that. Okay, so I replace these two things, which is quite complicated, by something more easily, and with only one equation. It's really our problem here. It's two equations at the same boundary. So in that puzzle us, but if we make this change of variables here, we get only one equation here. And why we call that time dependent? Because we don't see no time anymore. It's if I know I want to find directly these boundary conditions to prove. So I know this one is integrable, because for the small q, I know it's integrable. But I want to show directly it is integrable without the small q. So that I can do a gauge transformations on the Lax pair. So to go from the small q to the big Q. So I want to transform this L with small q to the same one, but big Q. And I remind you, for Q naught, this transformation is not linear at all, and it's quite complicated. But we can do conjugations from this L by these matrices here to go from this one to this one. But if I change, if I make a gauge transformations for my Lax pair, my K matrices is also transformed. Okay, I have a small k minus 1. Sorry about that, but if I remember, I have these K matrices. I must also make the same gauge transformations on the K matrices. And if I do that, the K matrices here now depend on the field Q naught. Previously, it depends just on some constant A, B, C, D. Here, it depends now on the field. And if I remember, use the reflection equations is here. Okay, that is the usual one, and I solve it for things. But this K matrices doesn't satisfy these things here. No, because they contain field, we must transform these equations when we call the dynamical reflection equations, where the left-hand side of the equations is exactly the same, but we must replace this 0 by the Poisson bracket of the K matrix. So you can show that by direct computations. No, taking these K matrices satisfy these equations. And if I don't wrote it, but if you wrote the transfer matrices with this big K and with the L with the big Q, we can show still the transfer matrices commutes. And it's why we call the boundary dynamical, because now the boundary, the K matrices encoding my integrable boundaries now satisfy some Poisson bracket. So now I want to solve. So just I have no time, and maybe we need 2 or 3 or 4 hours to explain how to solve this type of method and what is the modern techniques to solve. So this technique is now called the inverse cat-tree method. It's very well known, but it's quite complicated, and I have no time to explain all of that, but just to give you the idea. So really this method is like a Fourier transform, but for non-linear equations of motions. So that is really an equivalent of things to have the idea. And when I want to study the n-soliton solution, just to give you an idea of the formula works, if so I want the n-soliton, so what I showed you previously is for n is equal to 2. I have my Fourier transformations, if you want, contains n complex number, which is linked to the speed of the solitons, and another complex number called the norming constants, which is more linked to the positions where the solitons are in the space. And when you have all these 2n numbers, the formula for the soliton, the n-soliton solutions, is just explicit. It's not so easy to follow, but you see Q JT is given by 2 determinants, okay, where the determinant PB is, so the matrix PB is this matrix, just C is some 1, okay, it's just some a row of 1, the 1 here is some 1, and P, the entries of P is here. So C lambda K is my number I give us at the beginning, the norming constants. The lambda K, you see, it appears here and here, and you have an explicit formula. So that is the entries of my matrices, of my matrix P, which is here. I transpose, I take the determinant over the other determinant of this small matrix P, and that gives you a knowable formula when you wrote explicitly, what I showed you previously, but it is the solutions of the Ablovitz-Ladig problems. No, that is on the line. It's what I wrote here. That is a formula well known for the line. When we want to put some boundary, here you have some complications. And what we did, it's the equivalent of the mirror image problems. Okay, if I have something with boundary, for example, in electrostatic, we have the metal, we have our charge, and we just make an image of this charge and compute the field on all the plane. Here it's exactly the same thing, but because it's non-linear, it's what is called the non-linear mirror image. But okay, it's also technical, but okay, the idea is just that. It's just okay. I solve something on the line, I particularize it, and it will satisfy my boundary conditions. So previously, when we want to make this image here, that will be a 4 soliton solutions on the line. I have really 1 here, 2, 3, 4 solitons on the line, which cross on the line. But 4 solitons, meaning I have 4 parameters lambda k. And such that these solutions satisfy our boundary conditions, we must link lambda k and another lambda k. So choosing correctly these parameters, thanks to the nonlinear mirror image, we can just say this guy also satisfies the boundary conditions we want. And we can also change that. It's just another picture we get. And what we did, it's okay. That is the work of Carlos. It takes quite a long time to really implement the nonlinear mirror image for this new time-dependent boundary conditions. Because it depends on time, we must generalize all the previous methods, but we succeed in doing that. And well, we are quite happy to find that at the end, we succeed to finding new type of solutions thanks to that. And really, we find some solutions where no, it's given just by a 3 solitons. Okay, that is 1 solitons, 2 and 3 solitons on the complete line. And choosing correctly all the speed, we find that they satisfy our time-dependent boundary conditions. And that is two examples. So when the solitons, which is absorbed, go slower than the one which is reflected, for example. So here it's 1 reflected, 1 absorbed. We have also the other way, where the soliton which is absorbed is go faster than the one which is reflected. And you see it's not exactly the same type of picture, because here, for example, this one doesn't never cross the one, but everything works well. So we are quite happy with that. And something I need to say, it's the speed of this soliton is really given by my boundary parameters. So I cannot choose any speed. So it's why some is reflected, some is absorbed. So the one which is absorbed is really the speed of this one, and the c lambda k, the norming constant of this one, is really chosen such that it fits with the ABCD, which is in the boundary. So I cannot choose any speed of soliton which disappear in the boundary. And I don't draw a picture for that, but we can also emit at the same way. You just reverse the plot and it will work. So we can also emit some solitons from the boundaries. So in fact, I go fast because I saw okay, it's not a problem. So like I said previously, my solitons, I have only one speed when I want to absorb it. So we can ask yourself, can I have more general boundaries such that I can have 2 different speeds? So that is some very recent result we get. So now we solve the dynamical reflection equations for another, and we find a new big K matrices. We compare the Hamiltonians. We implement again the mirror image, and we have now, instead to 4 parameters, we have 6 parameters. And in fact, we have 2 speeds of solitons which can be emitted or absorbed. So here you see you have not the same speed, and that's these 2 speeds are linked to my 6 parameters at the boundary.
May I ask something?
Yeah, of course.
I don't understand how the boundary is moving. Is it moving at constant speed or what?
No, it's time dependent in the sense the boundary depends on the field.
That you said it's a time-dependent boundary.
Yes, because
at which speed is the boundary moving?
So it's not in this sense. It doesn't move. It's at the boundary conditions you put depend on the field. It's really the way to understand that is my K matrices depend of the field. So the boundary doesn't move. The boundary is still at the site 0.
So what is changing depending on the solution?
I Could you repeat the questions, please, John?
I thought you meant that it's a time-dependent boundary, but now you're saying that the boundary is somehow dependent on the solution, but in what way?
It satisfies, I cannot just say more than that, it satisfies these equations. So you see that is the bulk, the Laplacians, the things in the bulk, and the boundary conditions is not given by that. If you don't like time dependence, it's really because of the integrable system and the K matrices now as a non-Poisson bracket.
Now, I guess I just don't understand, why do the capital Qs somehow tell you something about the boundary? The boundary is
because you have this equation of motion, these equations, which is must satisfied by the field at the boundary. You see that is a site -1, 1, 0. So you have something like when you say, normally you say for the Dirichlet boundary condition, you say Q naught is equal to 0. That is a boundary.
So we should understand the little q's as the dynamical lattice points, or the points that are moving, and the big q's are located on this.
No. Big Q is small q and big Q is just a change of variables. It's the same. It's a field, but you change variables of the field. You change
so it's the boundary because it's Q0.
Yes, at the boundary. Yes, you change the field just at the boundary. Why we make the discrete case before the continuous case? Because that on the continuous case will be some direct functions, and it was not so easy to deal with it. So here it's discrete, so it's really at the boundary, I change the functions like that.
So I'm not sure what you're imposing on Q0. You're making it
the small or the big one.
But are you giving a specific time dependence to Q0?
No. It's really, you have an equation in the bulk. So J positions, and that I don't want, but it depends on time also. Okay, so that is a function of J and time. So that gives you the first derivative in time of the Qj. And J goes to 0 up to n-1. So in the bulk, you have this equation of motion. And you ask more these equations at the boundary. Like you ask Q naught is equal to 0 usually. For Dirichlet, you will ask Q naught, this Q naught is equal to 0.
And the lattice is infinite or periodic?
This one, half infinite.
Half infinite.
You go from -1 to infinite. You get the soliton solutions. It's usual things. It's to prove integrability, you remain since finite things, and after you send to infinity is one side or the both side, periodic things. So when I draw this picture, I'm really on the half line, and so I have a boundary outside 0, and this. So that means you look at this time here. For example, at this time here, you look Q naught, Q1, Q2, Q3, Q4, Q5, and so on. They satisfy the equation I showed you.
So you're drawing a continuous line, but it's really only defined at the integers, right?
Yes. So to draw the picture, I go to the continuous case, in fact, because it's more easily to draw and it's nicer to show. So to draw pictures, sorry for that, I draw for the continuous case. So it's really, you know, I can take a limit, a continuous limit, and I draw the continuous limit. Because if I show you some point, it's not so nice to show.
Okay, thank you.
Okay. So,
Nicolas?
Oui.
Would it be enlightening if you, or what would happen? You said that when your boundary is just symmetric, when you don't have these extra parameters.
So this one, no, previously?
No. You said, well, we wanted to solve the more general boundary condition.
Yes, this one here.
Yeah. If C and D are equal to 0.
you get
What happens? Why don't you need this change? Could you illustrate? I suppose you don't need that change of variable.
You don't need, because you will have not these equations. You see, if C is equal to 0, that disappear.
Okay.
And all the things here disappear, I think, if I remember correctly. And the boundary conditions will be Neumann, Dirichlet, or Robin. A over B will be, I don't know if you know Robin, but it's derivative proportional to the field. And the proportionality coefficient will be A over B. And okay, it's Robin conditions. And in fact, when these two guys appears, really we have in the mirror image, we have one more solutions, which allows us to have these emissions and absorptions. And why I like, in fact, I have before we make all the computations, I say, okay, because it's non-diagonal here, I must create or annihilate something. Because really, if you think about spin, for example, that annihilate my spin and so on. So that boundary conditions appears also, for example, in quantum mechanics. And this type of boundary, you have something which disappears or appears. And yeah, we work quite a long time to arrive to this conclusion at the end, saying, okay, no, I put that, I make this change of variables. I get this type of boundary, which was found before us, but differently, but that doesn't solve it. And after, we must find a new type of way to solve that. So we generalize the mirror image. And when we did that, we can have this type of solutions. And yeah, and so yeah, and the last point I would like just to say, no, so that is work in progress. It's really exact result we get. So we are going to publish that soon. And another question, which is more complicated, no, it's the quantifications. That means all these models I show you, Ablovich-Slavic or Schrödinger linear, are quantum counterpart, and we don't know how to quantify and if we can have creation of annihilations of particles in quantum integrable system or quantum field integrable system. And that was a surprise somewhere, because when you look somewhere for the definitions of quantum integrable field theory, somewhere the number of particles is conserved. So maybe we hope with these things, we are going to break that and to make some particular particle which appears, which is quite nice, because I never study quantum integrable field theory, because for me, we study field theory because we want to study something which the particle is not conserved. So for me, why make quantum field integrable systems? I never understand that somewhere, but maybe in this case, it will be useful. And so thank you.
Thank you very much, Nicolas, for the nice talk.
Welcome.
So we have time for questions. If you have any questions, just raise your hand, or maybe you can type in the chat. Okay, Julian first.
Of a single soliton.
Sorry, I don't.
Can you have like absorption or emission of a single soliton without the other one?
Yes.
Okay, and is that particular to your model, or was it possible without your special boundary conditions?
It's particular. We think to time-dependent boundary conditions, but I try to explain that. But yeah, to some more general conditions when the K is full, so the K matrix is full. If you take Robin boundary conditions, you have only the case when you have an even number of solitons on the line, and the mirror image go to n soliton, and always reflect.
John, next.
Yeah, so in the usual standard soliton theory, one gets these ratios of determinants of exponentials, but I mean, they come from a particular solution method, which is the inverse scattering method.
Yes.
And it really corresponds to a very particular choice of the integral operator that's involved. So that one usually has either finite or an infinite dimensional integral equation, and then one looks at things with finite rank, and it just gives you those ratios of determinants of exponentials. Yes. You just essentially pulled it out of the hat, but is there a systematic way to derive this using inverse scattering theory?
So what we use really, it's okay, we start from the things which is known on the line. So that is really well known from 30 years ago, I think, something like that. It's really, I take that from a thing, and after we must make the mirror image techniques. So mirror image techniques means we must fix, so I start from the solutions on the line, and I fix the lambda k and the c lambda k such that the Q will satisfy our boundary condition. So that is more developed by, for the usual boundary condition was developed by Abibulin, I think in the 90s. I think it's quite, yeah, it's okay, and by Sklenin and so on. But yeah, for when the K matrices and so on, and for our boundary, we must generalize some technical point, and I don't want to go on the detail because that becomes quite long things. But yeah, we must generalize at some different point the mirror image such that to get these solutions and to deal with this boundary.
So you don't really make use of the full apparatus of the inverse spectral theory. You just adapt solutions that are already defined on the half line and put in order to satisfy your boundary conditions using exactly. Mirror reflection.
Yeah, exactly. Okay. But the adaptation is not so easy to do.
No, of course. But it would be nice if you could derive these formulas ab ovo out of the Lax equations using inverse spectral theory.
But in fact, to make the mirror image, you use Backlund transformations. The Backlund transformations will be the way to understand the mirror image. So you deal with that, and the Backlund transformations is directly linked to the K matrices. If you know about Backlund transformations, it's what we did. So to construct that is also a way to use Backlund transformations, and which satisfies some differential equations. And to deal with, usually we put some boundary condition at infinite, saying the field is 0 to infinite. And here we must say something about the boundary. And that was done previously, but just for diagonal boundary. And to deal with the full matrices was quite complicated, and it's the work of Carlos. I must say that. It's really the work of PhD students which make all this work.
Well, in the inverse spectral theory, the Backlund transformations are interpreted as adding bound states or adding poles to the spectrum. And they can be also, of course, this goes back to the 19th century, they can be obtained directly by by writing down the Backlund transformation equations and solving them. And it turns out that if you have a particular solution, let's say, a vacuum solution, the adding of the solitons one at a time is actually an algebraic procedure. It's something that involves a nonlinear superposition of solitons. Yeah. So I don't know if you have all of that apparatus.
We have all of that. So if you want, when you have reflections, the usual one here, what we did is really, we had two solitons at the same time, such that, so I don't write here, but normally that if you plot it's really two solitons. And we add two solitons from the vacuum, but very particular two solitons. The second one must link to the first one such that the boundary condition is satisfied. I'm not sure if I'm clear, but it's really, you have lambda 1 will be the first soliton, lambda 2 will be the second one. And if you want reflections, for Robin boundary conditions, it's not so complicated. I think it's lambda 1, if I remember correctly, lambda 1 must be minus lambda 2 star. And the C lambda 1 and the C lambda 2 are also connected by something quite simple. But to find exactly what are all these details, and in fact, if we don't need all these details carefully. We miss what we found interesting, the one where the soliton is absorbed. We can reproduce all the things previously when two soliton was reflected, but it's the fact we did all the procedure again. We succeed in finding, okay, we can just add one solitons, but carefully, the lambda of these solitons is associated to my boundary parameters, and it will satisfy my boundary conditions.
Okay, next question is from Raphael. Please go ahead.
So very nice talk, Nicolas, very interesting. Could you go to the slide with where you have the big Qs? Yeah, so I'm a little worried when I see like the denominator can blow up and I have these square roots that could be, argument could be negative. Do you see any problems when the parameters are such that you have these problems?
We are also very puzzled about that. So in fact, the real boundary conditions, it's, you see that I solve a second order polynomials. It's why you have the plus and minus and some square root. So the real boundary conditions, it's this second order polynomials. No square root, nothing.
Sorry, I missed it. Could you repeat?
So that is really, you see, that is a solution of a second order equations, second degree equations.
Mm-hmm.
And the real boundary condition is not that, that is a solution of this equation. So if I want to, I can write you something without square root and so on, and that is my real boundary condition. But it's more ugly because it takes 3 lines, second order, second degree equations.
So nothing strange happens.
No. And in fact, we really like here. You can also puzzle me about that, for example. But you even start at the beginning if you want. Sorry about that. I have some logarithm of 1 minus here at the beginning.
Mm-hmm.
And that, okay, we show the square root, the norm of the square root of the field is never greater than 1.
I see.
But good question. Maybe for, so that is really saying it differently. That is the Hamiltonian formalisms for the field such that the square root of Q is not greater than 1.
Mm-hmm.
But all the soliton solutions I show you, is it the case?
Okay, thank you.
Okay, thank you. Can I just ask a question myself? So on this slide, you have these non-canonical Poisson bracket.
Yes.
So presumably that means then that there's no Hamilton equations of motion for these variables. Is that correct? They don't satisfy Hamilton's equations.
I can make that canonical by taking some square root of 1 minus Q square if you want. But
okay, so you can make them canonical.
I can make it, but yeah, like you see, Raphael just say me it's the ugly square root of 1 minus Q. So we wrote like that, and to do the computation is easier like that. But you can make a canonical Poisson bracket with another with the same.
Well, that's just the Darboux theorem. You can make any Poisson bracket canonical if it satisfies the axioms.
Yeah. Right. Yes. Okay. And can you put a symplectic structure on this? So you use the Poisson bracket, but is it possible to?
That I don't know.
Okay.
That is very basic things. It just take this Hamiltonian, this Poisson bracket, you compute that like derivations, and you find the equation of motion.
But is there a center of the algebra or no?
Not sure. That is also not us. It's also it's Ablowitz and Ladik who did it like that. So
no, I suspect these are no. This is symplectic, and it only has constants in the center.
Yeah, I think so. Something like that. You can really, or you can use canonical things and everything. You don't ask permission.
Okay. Any last minute questions from anyone?
Maybe I will have one question, Michel. You have an elastic interaction between solitons. What is the angle between these solitons? Could you comment on it?
For example, the angle here.
Because you have an elastic one. What you have 2 solitons entering and 2.
So the angle is what I want. it's really given by the lambda one. So that is characterized by complex number, this one also. So I can choose the angle I want and it will be always elastic. The things we are interested in solitons is really, you see, when I follow that,
Yeah.
I have a shift here.
Ah, okay.
It's the same angle. So it's sometimes I forget if it's accelerated or slowed down, and you must compute more that. It's the things we compute. The angle remain the same, but okay, we have a delay and we compute this delay. And you see here also
That's what
is accelerated.
I mean, the angle is just the velocity, right?
Yeah,
exactly.
Yeah.
And you choose the parameters. So that's these, I guess, lambdas or whatever that tells you what velocity is.
But for this case, again, the velocity of this one is really given by the boundary. I have a boundary conditions that is with my parameter A, B, C, D. And if I want the soliton disappear in the boundary, the speed, the velocity of the solitons must be chosen very carefully. If I don't choose this one, it will be reflected. It's why I show you this type of picture. It's okay. I have some soliton which is reflected, and I have one which is just absorbed. I cannot have differentials. And that is what I say at the end. No, we succeed by making the boundary more complicated to have two different speeds where the solitons can appear or disappear and so on.
You're saying that there's one, or I don't know, more than one velocities where it just stops at the boundary.
Exactly. So in fact, we are quite excited by that because we can even say, okay, can we do that experimentally for really saying, okay, I choose this particular boundary and some soliton can disappear on the boundary, or I can emit a very particular soliton at the speed I choose. Saying, okay, I put this boundary, I emit this type of boundary, this type of solid, but okay, only one type for the moment. And that's why no, we try the other one when, okay, no, I choose. But here the boundary, just to say you, it's quite complicated, no? Even if you saw the previous one, this one is even worse. But we, okay, just to say we succeed in doing some integrable models when we can just emit two solitons with different speeds, with two given speed. And all the other one will be just reflected.
And you exclude the blow up, as I understand.
Yes.
Okay, interesting.
Okay, thank you. Any final questions? If not, let's thank Nicolas again for the very nice talk.
Thank you.
Thank you very much. And thank you everyone for attending. So have a good evening and see you next week.